For my video presentation, I'm going to be doing part of question 10.25 from the book, and it asks you to calculate the moment of inertia tensor for a cube, well, not a cube, a prism that is located with its center of mass at the origin of our axes. So it asks you to find I center of mass. So if we were to think back to our introductory physics, the equation angular momentum is equal to moment of inertia times angular velocity, but we now know that that's not true. It only holds in the cases where the angular momentum and the angular velocity are in the same direction, which is basically not very often at all. So instead, we're going to use this equation with the angular momentum vector times the moment of inertia tensor times the angular velocity vector. So if we look at what the moment of inertia tensor is for a moment, it is a 3x3 matrix in this case because we're in 3 dimensions. And across the diagonal, we have the IXX, IYY, and IZZ. And these are the moments of inertia. And then on the off diagonal, we have the products of inertia. And in this case, IXY would represent the x component of angular momentum when omega is in the y direction, and analogous conventions for each of the other ones. So we have to calculate all 9, but we'll see that there's a lot of shortcuts. So we might as well start with the first one, which is IXX. So the equation for this is the triple integral of y squared plus v squared times the density. So rho is our density, it's just mass over the volume. We're told that we have a mass m for the prism, and the volume are just the 3 sides multiplied together. And they each go from negative a to a, negative b to b, and negative c to c. So that's just 8 abc. And this is a constant, so we can pull it out of our integral. So we can also break up our integral into 2 pieces, one for the y and one for the z. So we'll have this integral plus this integral, and we're going to divide it even further and just look at the first half of our integral for IXX. So we can just start with the x component. The integral of dx is just x, and we're going from a to negative a. So when you plug that in, you'll get a 2a here, and one of the 2's will cancel, and the a will cancel, and you'll just be left with the integral from negative b to b, negative c to c, y squared dy dz. You can do that again for z. That's pretty obvious that it's going to have the same effect as the x. So we're going to be left with m over 2b is equal to the integral from negative b to b of y squared dy. When you find the antiderivative of y squared, you get y cubed over 3. When you plug in your limits of integration, you get this. So this becomes 2b cubed over 3. The 2's cancel out, and one of the b's cancel. So that IXX, half of it at least, is equal to mv squared over 3. But we've only done half of the integration. We've only done this part. So you repeat all the same steps, only using z squared, and it's easy to see that it's just a similar answer. This just becomes c squared, and you'll have IXX is equal to m over 3 times the quantity b squared plus c squared. So if I were a textbook, this would be the part where I told you to prove to yourself that when you do the analogous IYY and IZZ with different components in the integral, that you'll just get the very similar IYY is equal to m over 3 a squared plus c squared, and IZZ is equal to m over 3 a squared plus b squared. So we now have the 3 diagonal elements of our moment of inertia tensor, but we now need to calculate all 6 products of inertia, but we can see that it's really not that difficult. For example, we're going to take the IXY case, and we know the formula for this is just the triple integral of rho xy dx dy dz. So as before, rho comes out because it's constant. I started by taking the antiderivative of dz. As before, the z will cancel with that c, actually. The z element will cancel at c when you plug in the limits of integration, and you'll just be left with this, this integral, and I've already taken the antiderivative of y squared. And this is when we get an interesting result, because when we plug in, antiderivative of y gets us this. And when you plug in your limits of integration, you'll get c squared over 2 minus negative c squared over 2. So these two elements cancel out, and you'll get 0. If you did the x one first, you would get the same result. So this product of inertia is equal to 0. So you could calculate all the other ones, or you could just think for a little bit and try to be a bit clever. And we know if in the x equals 0, y equals 0, and z equals 0 planes, if there's reflective symmetry in two of those planes, then all of the off-diagonal elements are 0. And in this case, all three of those planes have reflection symmetry. So we know that all of the other elements are equal to 0. So that leaves us with a final answer of the moment of inertia tensor amount for rotations about the center of mass is equal to m over 3 times our diagonal elements, with all other elements equal to 0. So when we look at this, we realize that we have a diagonalized matrix, and this means that the three axes that we chose are actually the principal axes for this system. And that means that the rotations about those three axes will cause the moment of inertia to be in the same direction as the angular momentum. And we can see that with just a quick, easy example. If we multiply our moment of inertia tensor times omega when it's only in one direction, the answer, our angular momentum, will just be the ixx component times our angular momentum, which shows us that the angular momentum and the angular velocity are in the same direction. And that's it.